So in this video, we'll introduce two foundational probability rules, the sum rule and the product rule, and that it will also give rise to the important rule that's called Bayes rule, that correspond to the algebraic addition and multiplication, if you like, that are quite essential and coming, very frequently in many of the topics that we'll be discussing in machine learning and AI. So I would like to introduce those using, if you like, a simple experiment. So I have here in this experiment two urns or containers. So this is container, let's say 0, and container 1. And I will be symbolizing with the letter Y these containers. And these containers contain sort of widgets of two types. One is a black widget, and the other type is a white widget. It doesn't really matter how many at this point. We don't really count the widgets to learn about this kind of rules, so it just doesn't really matter. Okay, so we have here, so the experiment goes like this. So the first step of the experiment is to pick up randomly a container, not to pick up, but just pick a container, randomly a container. And as we said that we will use the random variable name y, which is evidently binary random variable. It can only take values 0 and 1. And we put our hand inside that kind of container and we take out a widget and we open our hand and then we reveal the identity of the widget, and we will put it back from the widget that it came from. Okay, so we effectively sample a widget with replacement. The random variable for the widget is going to be x, and obviously x will be, let's say, 0 will correspond, let's say, to the black widget, and 1 will correspond to the white widget. Okay, so that's basically the mapping that we have implemented, and there is a random variable to govern that kind of sampling kind of process. So the with replacement is a common term in sort of sampling, and means put back the widget to the container we came from. And actually the reason why we need to do that is because we do not want to change in the statistics of the problem over time. By putting it back, then we have the same probability of picking up a widget of a specific type out of each container. So the problem is kind of stationary. The other thing, of course, they are giving us before we start asking questions is we are giving some kind of what we call marginal probability, just a probability distribution of y, and this is P of y. And as you might expect, the probability distribution of y is a sort of discrete, y is a discrete random variable, so therefore we expect to see some kind of a plot like this, where this thing is 0.4 for when we have a container 0, and this is evidently 0.6 when we have container 1, because the summation of the two has to be equal to 1.0 to be a proper probability distribution. So what it basically says in English, this graph is translated is that I have some preference to select containers, and in fact I'm not selecting containers with equal probability. I have some kind of a preferential bias towards container 1. Okay, could be anything. All right, so here comes the first question. The first question is, can you tell me anything about the P of X? So we, first of all, we can definitely suggest that because we have two types of widget and X is a discrete random variable, we expect to see something like that. Maybe this is the other way around, but we definitely expect to see something like that. We just need to specify the heights of these two sort of probabilities. So to estimate the probability, of course, we will be executing this experiment. We will be executing the experiment. Let's call this execution that happens n times of both of these kind of steps. And let me just also plot over here the diagram. We have definitely four possibilities here that can happen. So if this represents the X random variable and this represents the Y random variables, we have an experiment that involves two random variables, X and Y, and all the events are joined. So this means that X happens, let's say, first the Y happens, where we have, let's say, select a container, let's say 0. And then the X happens, let's say I take a black widget out of that kind of container. So X Y can be 0 or 1, and therefore X can also be 0 or 1. And therefore, what I'm actually representing here with dots is the joint events. Okay, something like that. Okay, so, and of course, what I would like to do is I want to give you also the counts that I have obtained here. I will call this count N00, this count N01, N11, and N10. Okay, so that's basically the count, the counts that I obtained. And now that I have obtained the counts, I will be able to start, making some kind of thoughts about how to estimate the P of X is equal to 0. So I'm going to write it over here. P of X is equal to 0. Well, X is equal to 0 can happen in when two things are happening. First, it can happen when I have selected, so a black widget can come either from the container 0 or from the container 1. So definitely the number of times that I've obtained a black widget is when I add the N00 and N01 and I divide it by N. And this is basically the first thing that I can say. Also, I can say something similarly about P of X is equal to 1. I can say that this can come also from the 0th container or from the container 1. And this is fairly intuitive. And so I can definitely generalize these two. So this was N00 plus N01 divided by N. And then this is N10 plus N11 divided by N. I have answered the question that they're asking me to answer, but I would like to generalize what I have done over here into the following rule, which I'll call the sum rule. I would like to say that the P of X, which gives you the probability distribution of X, is a summation. Here you see two terms in the summation because I have a random variable y which can only take two values, but in general it's a summation over all values of y of the joint probability distribution of X and Y. Similarly, I can answer problems. I know that right now the problem gave me the P of y, but in general, I can symmetrically do this as well. So if they didn't, and they gave me something about x, I can definitely respond something about, I can definitely say something about P of y. So this is the so-called sum rule. And it's also known as the marginalization rule that allow me to do the following. If I know I'm giving some information about the joint probability distribution, I want to take some of these random variables out, I will sum over them. And therefore, this will allow me to obtain the so-called marginal probability distribution associated with this joint probability distribution. So that is the first rule that I said is the equivalent of addition, but in the probability, algebraic addition, but in the probability domain. So now the second question comes, and so let me just separate the second question over here. So the second question is, can you tell us anything about the P of y given x? Now this is a probability distribution that's actually called conditional probability distribution, and it's symbolized with this symbol over here, this vertical line that separates a random variable from another, but this the other random variable, the x more specifically in this case, because it's coming after that symbol, which is actually called given. It's a fixed quantity, it's given, so it's not random variable anymore. Okay, so that kind of have some kind of implications onto how we count in order to come up with the specific values of these conditional probabilities. Now, definitely we have 4 possibilities in this conditional probability. The first possibility, and let me write down on the right side these possibilities, is when the 0th container is selected, given that I had seen a black widget. The second possibility is the container 1 was selected given that I have seen a black widget. And the same things for the white widget. Okay, so these are all the 4 possibilities I have in this problem. I have 2 binary random variables. Evidently, when I have non-binary random variables, there are many, many more possibilities. But definitely I can actually start addressing the first one, and I can definitely say that something about it, given the fact that I was given the counts. Now, we need to be slightly careful here, because you want to consider this given the x is equal to 0 to effectively constrain the space over which you are executing this experiment. So given that x is equal to 0, you're actually, instead of dividing by capital N, you are dividing over the summation of n00 and n00 and n01. So this will act as a constraint. So your denominator is this, because you only look for x is equal to 0. And then evidently, the numerator is when y is equal to 0. Well, when y is equal to 0, you're looking at the n00 count of events. And that is basically your response. That is going to be your result, if you like, which is a number. Similarly, with similar kind of considerations, you will actually do the others. Let me write them down quickly. P of y is equal to 0 given x is equal to 1 is n10, n10 plus n11. And finally, P of y is equal to 1 given x is equal to 1 is n11 divided by n10 plus n11. And now we can actually, similarly to what we have done kind of earlier, we can start to understand how we can potentially start generalizing this into that what will end up being called the product rule. And let me just do that from this equation. So let me call this 1. And I'm saying from 1, I can write that n00 is equal to P of y is equal to 0 given x is equal to 0 times n00 plus n01. A simple modification from a simple product of that expression. Okay, and then what I can actually see also is I can replace this with something that I have seen earlier. So earlier I have seen that P of x is equal to 0 is equal to n00 plus n01 divided by n. And therefore, I can actually, from these two, I can get that the n00 is equal to P of y is equal to 0 given x is equal to 0. And I will be replacing this n00 plus n01 with P of x is equal to 0 times n, with P of x is equal to 0 times n. And therefore, I can write that n00 divided by n is P of y is equal to 0 given x is equal to 0. But n00 divided by n is the probability of y is equal to 0 and x is equal to 0. And therefore, I just wrote it as a product of the conditional P of y is equal to 0 given x is equal to 0 times P of x is equal to 0. So this is basically one expression I got out of the first equation over here. I can actually do the same for equation 2, 3, and 4. And this will actually allow me to generalize. And if you see the form over here, I am writing something like the joint is equal to some product. So let me write down the generalization of this formula, which I'll be calling the product rule. And the product rule says that P of x comma y is equal to P of x given y times P of y, or equivalently P of y comma x is equal to P of y given x times P of x, which is basically what we had done just now with x. In our problem, someone gave us the x and wanted to find out, sorry, someone has specified the x and wanted to find out the conditional P of y given x, and that conditional is definitely the joint divided by the P of x, which we already have calculated from the using, if you like, the sum rule. So this is the product rule and will allow us to actually do a lot of things, this product rule. In some instances, in many problems, we have been given, if you like, a joint. We know information about the joint, but we would like to factorize the joint into some components, hoping that some of these components were simple to estimate. So this is the main usage of this rule in estimation problems that we will see. But in addition to that, it also defines a very, I will call it a foundational kind of rule that we'll call the Bayes rule as follows. Given that P of x comma y is equal to P of y comma x, we do not really change anything by swapping the variables around. And effectively, you can actually see that also in the diagram because effectively they point to the same quadrant. So we can actually do the following. We can actually write here that P of x given y times P of y is equal then to P of y given x times P of x, or P of y given x is equal to P of x given y times P of y divided by P of x. So this is called the Bayes rule. And some of the components over here have taken the sort of following semantics in this kind of discussion. This is called evidence. It tells a story about the data. This is called prior, and it allows us to tell us something about the why before we actually start any experiment. And this is actually what had just happened in our case. Someone gave us some information about the why. And this is a very important quantity called likelihood. And tell us how likely is the data that we are seeing X as given the fact that we have a specific value in the y variable. So we will see this rule over and over again in this course. More specifically, this probability distribution kind of encompasses the whole domain of machine learning, more specifically supervised kind of learning, but also some others. And in our case, X will actually be the data that someone is giving us. Let's say X is an image with, let's say, a person in there. And Y will be, let's say, 1 when there is a person, or 0 when there isn't. So in many of our discussions inside the perception system, we'll actually have these many examples, and someone will actually ask us to do predictions as to the presence or not, let's say, of a person on an image, and this prediction will be fully quantified using this conditional random variable, this conditional distribution. So we will be making predictions, the so-called y-hats, from using this conditional probability distribution, and that's why this kind of rule is quite important, because it will allow us to do this prediction, despite the fact in some instances we'll be potentially not have any prior information. We have a uniform prior, or we will not necessarily engage this actually rule, but we will be working only with the likelihood. I think it's a good idea to actually know this rule by, to understand it and know this kind of rule, as well also the other two. In fact, this rule was derived out of the product rule.